I want you to think about a question. Not a complicated question, not a technical question, just a simple, honest question that I suspect has crossed your mind at some point in your life. If the Big Bang created everything, the matter, the energy, the space, the time, what was there before it? What existed before the universe began? Now, most people expect one of two answers. Either nothing, a kind of empty void waiting for something to happen, or some other universe, or some other existence, stretching back before ours. But here's what I want to tell you right at the start of this lecture. Both of those answers might be wrong. Not because we haven't looked hard enough, not because the technology isn't there yet, but because the question itself, what came before, may not mean what you think it means. And by the end of this lecture, you'll understand why that's not a cop-out. It's one of the most profound insights in all of physics. My name is Dr. James Mitchell, and this is Science Explained Properly. Let's begin. Before we ask what came before the Big Bang, we need to be clear about what the Big Bang actually was, because there's a common misconception worth clearing up immediately. The Big Bang was not an explosion, not in the way we normally use that word. When most people hear Big Bang, they picture something like a bomb going off. A single point in space, a tiny, dense ball of matter, suddenly exploding outward into a surrounding void, expanding into emptiness. That's not what happened. The Big Bang was not matter exploding into existing space. It was space itself expanding. Space, along with everything in it, stretching outward in every direction simultaneously. There was no surrounding void for it to expand into. There was no outside. Space didn't expand into anything. Space itself grew. Think of it like this. Imagine drawing dots on the surface of a balloon. Now inflate the balloon. The dots move apart, and not because they're traveling across the surface, but because the surface itself is stretching. Every dot moves away from every other dot. There's no center of expansion. There's no edge. The surface is simply getting bigger. The universe is that balloon. Except instead of a two-dimensional surface, it's three-dimensional space. And instead of inflating into a room, it's expanding into, well, nothing, because there is no outside. Now, here's the key point for our lecture today. If the Big Bang was not an explosion into existing space, if space itself began at the Big Bang, then what does before even mean? This is the heart of the matter, and it's where physics gets genuinely strange. We think of time as a river, always flowing, always moving forward, stretching backward into the past as far as we care to imagine. Before yesterday came the day before last year came the year before the Big Bang came. Well, here's the problem. Time, as best as we can tell, did not exist before the Big Bang. Not because something destroyed it, not because it was hidden somewhere, but because time is a property of the universe, not a container the universe exists inside. Time, like space, like matter and energy, began at the Big Bang. Or more precisely, the concepts of space and time as we understand them broke down at and before that moment. Here's an analogy that helps. Imagine you're standing at the South Pole. Someone asks you, what's south of the South Pole? The question sounds reasonable, but it's actually meaningless. The South Pole is the southernmost point that exists. There is no further south. Not because there's a wall there, not because something is blocking the way, but because south, as a direction, stops being meaningful at that point. The Big Bang is like the South Pole of time. What came before the Big Bang may be as meaningless as What's south of the South Pole? Not a mystery waiting to be solved, but a question that dissolves when you examine it carefully enough. Now, and this is important, this doesn't mean physicists just shrug and move on. Because while the question, what came before, may be problematic, there are legitimate scientific theories about what might have given rise to the Big Bang. And some of them are extraordinary. Before we explore those theories, let's be honest about something. Our understanding of physics breaks down at the moment of the Big Bang itself, not just before it, at it. We have two extraordinarily successful theories of how the universe works. The first is general relativity, Einstein's theory of gravity and space-time, which we discussed in our gravity lecture, and quantum mechanics, the theory of how matter and energy behave at the smallest scales, which we touched on in our light lecture. Both theories are spectacularly accurate in their own domains. General relativity describes the very large, planets, stars, galaxies, and the fabric of space-time itself. Quantum mechanics describes the very small, atoms, particles, photons, and so on. But here's the problem. At the moment of the Big Bang, the entire universe was simultaneously incredibly small and incredibly massive. You need both theories at once. And when you try to combine them, when you try to apply both general relativity and quantum mechanics to the same moment, the mathematics breaks down. You get infinities, nonsensical answers, division by zero. Physicists call this a singularity, and it's essentially the universe's way of telling us that our current understanding is incomplete. We're trying to read a book, but the first page is missing. We can see everything that came after page 1 with extraordinary clarity. But page 1 itself, the moment of the Big Bang and what preceded it, is beyond our current ability to describe. What we need is a theory of quantum gravity, a framework that combines general relativity and quantum mechanics into a single coherent picture. But we don't have one. Yet. String theory is an attempt. Loop quantum gravity is another. But neither is complete, and neither has been experimentally confirmed. So when physicists talk about what happened at or before the Big Bang, they're working at the very edge of what science can currently say. These are serious, mathematically rigorous theories, but they are not yet confirmed. Keep that in mind as we explore the theories. The first major theory is called eternal inflation. To understand it, we need to talk briefly about something called cosmic inflation. In the very earliest moments after the Big Bang, we're talking about an almost incomprehensibly tiny fraction of a second. The universe underwent a period of extraordinarily rapid expansion, faster than the speed of light. In a blink, a region smaller than a proton expanded to roughly the size of a grapefruit. This is called inflation, and there's strong evidence it happened. It explains several features of the universe we observe, why it looks the same in all directions, why it's so flat, why the cosmic microwave background radiation has the pattern it does. Now, the theory of eternal inflation takes this further. It suggests that inflation, once started, never completely stops. Imagine a vast, infinite quantum field, a kind of cosmic landscape stretching in all directions. In most of this field, inflation is happening constantly and rapidly. But occasionally, randomly due to quantum fluctuations, a small region of this field stops inflating. That region becomes a universe, our universe, a bubble of non-inflating space in an eternally inflating sea. And here's the extraordinary implication. If this is correct, our universe is not the only one. The inflating field produces bubble universes constantly and randomly. an infinite number of them, each one potentially with different physical constants, different laws, and different histories. This is what physicists call the multiverse. And our Big Bang, the beginning of our universe, was simply the moment our particular bubble stopped inflating and settled into its current state. So, what came before our Big Bang? On this theory, it was the eternally inflating field that gave birth to it, an infinite landscape of quantum fluctuations, endlessly producing universes, including ours. The second major theory takes a completely different approach. What if the universe doesn't have a beginning at all? What if it cycles? The cyclic universe model, developed by physicists Paul Steinhardt and Neil Turok, proposes that our universe goes through endless cycles of expansion and contraction. Each cycle begins with something like a Big Bang, expands, cools, and eventually, over trillions of years, contracts back to an extremely dense state. That contraction triggers a new Big Bang, and the cycle begins again. On this model, before the Big Bang isn't empty or meaningless. It's the previous cycle of the universe, an almost identical cosmos, expanding and contracting, stretching back through an infinite series of cycles. No beginning, no end, just an endless oscillation. Now, there's an interesting modern version of this idea connected to string theory, involving objects called brains. Brains is short for membranes, which are higher dimensional surfaces on which universes like ours exist. In this picture, our universe exists on one brain, and there's another brain parallel to ours in a higher dimension. Occasionally, over vast timescales, these brains collide, and the collision is what we experience as a Big Bang. It's a remarkable idea, and while it's speculative, it's mathematically serious and actively researched. The third theory is perhaps the most mind-bending of all. What if the universe came from nothing? Not nothing in the everyday sense, not an empty room or a dark void, but genuine nothing. No space, no time, no matter, no energy, no laws of physics. Absolute nothing. Your instinct is probably telling you that something can't come from nothing. That's a reasonable instinct. But quantum mechanics has something surprising to say about it. We talked in our light lecture about virtual particles, pairs of particles that pop into existence from empty space and annihilate almost instantly. This happens constantly, everywhere in what we think of as empty space. Space isn't truly empty. It's fizzing with quantum activity. The physicist Lawrence Krauss and others have proposed that something similar could apply to the universe itself. That the universe is, in a sense, a quantum fluctuation. A fluctuation in whatever preceded it. In the framework of quantum cosmology, developed by physicists including Stephen Hawking and James Hartle, the universe doesn't have a boundary in time at all. They proposed something called the no-boundary proposal. The idea is that when you go back to the very beginning of the universe and apply quantum mechanics to time itself, time smoothly transforms into a spatial dimension. The universe in this picture has no edge, no beginning, no moment of creation. It simply is. Finite but unbounded, like the surface of a sphere. A sphere has no edge. You can travel across it forever without reaching a boundary. But it's still finite. The universe in this model is similar. Finite in time, but with no beginning. No moment before which you could ask what came before. Here's where the South Pole analogy returns. In this model, asking what came before the Big Bang is precisely like asking what's south of the South Pole. Not unanswerable because we lack information. Unanswerable because the question itself breaks down. Now, let's be honest about where all of this leaves us. We have three serious scientific theories about what preceded or gave rise to the Big Bang. Eternal inflation, an infinite quantum landscape that endlessly produces bubble universes, of which ours is one. The cyclic universe, an endless series of expansions and contractions with no beginning and no end. The no-boundary proposal, a universe with no beginning at all where time itself transforms near the Big Bang. And the honest answer is, we don't know which, if any, is correct. We may not know for a very long time, possibly ever, because the nature of these theories makes them extraordinarily difficult to test. If other universes exist in an inflating multiverse, we may never be able to observe them. If previous cycles of the universe existed, the evidence may have been washed away. If time itself had no beginning, the mathematical picture may never fully translate into observable predictions. This is one of the places where science reaches its current frontier, not because scientists have given up, but because the universe is under no obligation to be easy to understand. And here's something I want to say about that. The fact that we can even ask these questions, the fact that human minds on a small rocky planet orbiting an ordinary star can construct mathematical frameworks that reach back to the very origin of everything. That is not a failure. That is one of the most extraordinary achievements in the history of thought. Let's bring this together. We started with a simple question. What came before the Big Bang? And what we've found is that the question is harder than it sounds, not because the answer is hidden, but because the framework we use to ask it, time, before, after, and the idea that every moment must follow from another, may not apply at the boundary of the universe's existence. Time began with the universe, or transformed at its birth, or has always cycled without beginning or end. We don't know which, but we know this. The universe we inhabit, this vast, structured, luminous cosmos, emerged from conditions our current physics cannot fully describe. And that gap in our knowledge is not something to be embarrassed about. It's an invitation, an open door. The questions that sit at the edge of what we know are the most interesting questions there are. And I want to leave you with something personal. You have spent your entire life inside time, moving through it, remembering the past, anticipating the future. Time feels like the most fundamental thing there is, more fundamental than matter, more fundamental than space. It feels like the container everything else exists inside. But what we've explored today suggests that time is not a container. It's a feature, a property of this particular universe that emerged with everything else and may have had no existence before, which means the question, what was there before the universe, may be as personal as it is cosmic. Because the before you're imagining, that sense of time stretching backward into infinity, that's your mind, your experience, your consciousness reaching for something it cannot quite grasp. And maybe that reaching, that instinct to ask why, to push past the boundary of what's known, is the most human thing there is. We live inside the universe. We are made of it, and we spend our brief time here trying to understand where it came from. That's not a small thing. That's everything. In the next lecture, we'll turn from the universe's origins to one of the most mysterious and misunderstood concepts in all of science: what energy actually is. Thank you for listening. I'll see you in the next lecture.